Okay, so let's press on with the impacts. We're doing impact of Bragg diffraction. And so we just said that with n lambda is equal to 2 times sine theta, the Bragg condition, we can figure out the crystal structure between the different atoms. And if we do this over every material that we can, and then also back that up with theoretical explanations, we come up
Hmm.
with these unit cells. These unit cells are the pattern, it's like the simplest version of the crystal. So for our example up here, the simplest version of this crystal would be one, two, three, four atoms. Because if we take these four atoms, we call it a unit cell, like a basic cell, a building block, a little Lego piece. We can take this four here and we can translate it to the right. We get the same four. Translate it again, we get the same four. Translate it down, we get the same four. I guess I mean the same spacing.
Yep.
Okay, so we do theoretical and also experimental, experiments to verify this, and we end up with 14. There's exactly 14 Bravais lattices. These are 14 possible crystal structures in the universe. And
Is that
so
right? There's only 14?
there's only 14
That's been proven?
proven.
That seems weird.
Seems weird, right? Isn't cool, right? Because it seems weird. It's like, why shouldn't there be just an infinite number? But there's only 14.
Hmm.
The universe is simultaneously complicated and simple. Only 14.
Hmm.
Okay.
Okay.
Yeah. So you get triclinic. So it's a parallelogram, but in 3D, or a monoclinic, where it's a parallelogram in 3D, but they're specifically right angles. So I guess this is like a rhomboid,
Hmm.
etc. There's
Yeah.
several more, right? We don't need to go through them. But the key thing is we using the Bragg condition from Sir Lawrence Bragg, we figured out that there's only 14 crystal structures in existence.
Hmm.
Okay, now why is that useful? Because once we understand the possible crystal structures, we can really figure out how to lay down atoms exactly where we want them to be. Because it's not just heat the thing up and like bang it with a hammer and now you have a sword where the atoms are wherever, right? We can actually just grow crystals to be whatever we want them to be. And
Hmm.
so this one in particular, it's deuterated potassium phosphate, KDP. And this is a special crystal to me because it is nonlinear optics. Maybe I shouldn't go that far. It does some weird stuff. It does kind of magic stuff. It does energy doubling, and so it's used here in fusion reactors, where you have a bunch. This is an artist conception. You have a bunch of lasers coming in, and you have a pellet in the middle. And here it is. This is you have a bunch of lasers coming in. You have a tritium pellet in here, and then this gold pellet. I guess tritium target. You have this gold pellet that reflects all the lasers in. You jam a bunch of energy into a tiny little spot, and that's how you get fusion. That's how you get fusion at the National Ignition Facility in the U.S. And here, gosh, I don't know if you remembered this, but this was in the Star Trek movies. I think Beyond.
Yeah, I do remember that. Yeah. I
Yeah, right.
think it was Into Darkness.
Thank you. Into Darkness.
This was the engine room. Yeah.
The engine room, right? Right. And these are here. These are just these are. Here's a ladder for reference, and then
Yep.
this is a laser pathway that's going into
Hmm.
this sphere that deep down in there holds this little pellet. You focus this enormous amount of energy into a little tiny pellet and start fusion.
Right. And those big crystal structures, those big, like in that picture above,
Yes,
is used to help focus the beam, all the
exactly,
beams into that tiny area.
exactly. So
Mhm.
it's it does frequency doubling or maybe tripling, one of those. So you come
Mhm.
in with a low frequency wavelength, a low
Mhm.
energy light, and then you can send the light through this, and by the time it comes out, it has doubled in energy.
Right.
It's kind of
This,
some wizard stuff,
yeah, yeah. This woman measured the wavelength with her ruler.
with the ruler. There it is, right?
There it is. Yeah.
And it's kind of silly if you think about that. Like, oh, what is this ruler? I guess this
I
predates
mean,
banana for scale.
yeah. Also, it's like one of those elementary school rulers, like the wooden ruler.
Oh
It's
yeah,
not even
with this
straight.
crazy sharp metal edge.
Yeah.
You
doing
like
some
with your
science.
pencil, you like draw along the edge of the ruler,
Yeah,
and then you just have a bunch of graphite on your desk. Like, this is not what I wanted.
yeah, yeah. Yep, yep.
Okay, let's press on, do a little bit more. So once we, so that's one application of Bragg's law. We figured out how to do these crystal structures. We can start. We technology over the whatever many decades gets us towards fusion, and Bragg's law was an important part of this. Also, with these Bravais lattices coming from Bragg's law, we can start making some designer materials. This is
Hmm.
something that is only maybe the last 40 years, where here's lanthanum cuprate, so lanthanum, copper, and oxygen, sitting on top of lanthanum, strontium, aluminum oxide. And so, in the past thousands of years, you would have a block of copper, and then eventually you mix copper with aluminum. I think that's true, and then you get bronze. And then eventually you can refine steel. Then you can add carbon. You get carbon steel. Then you add some chromium. You get stainless steel. But all of those are really like this entire block is one type of material. But nowadays we can really lay down different layers of atoms as we want. So this entire block is lanthanum cuprate. This next one is a bilayer. So we grow first lanthanum, strontium, barium, calcium. This is one. These black dots represent some of this. It's mostly lanthanum with little bits of these other things. But then we can switch it up. We can switch it up and grow this next section, lanthanum copper oxide, or even I guess in a different case, even more precisely, we can grow one layer of the lanthanum copper oxide, and then a single layer of this strontium, barium, calcium, and then switch back to this lanthanum copper oxide. Why is this important? This isn't, or why is this? Why does this have impact to society? Because when you have these bulk objects, they have whatever properties you have of the bulk thing. If it's copper, it's going to be copper. However, if you take, say, copper up here and mix it and like mush it up to stainless steel, right at that interface, right where that crossover is, you get the properties of copper plus versus like interacting with the copper properties of steel, for example. I mean, these are different materials, but that's the idea. What happens? What happens right when those two materials touch? And some new physics, some weird stuff can happen, which could be future technologies. Um, additionally, if you have a large quantity of one type of thing, the properties are dominated by all these atoms in the middle. But what happens if you only have this interface? So what do you have if you only have the properties of this skinny little layer? The properties of this are no longer dominated by like the volume of stuff. It's only that outside layer, that the thin layer of whatever those properties are, which could be different than this bulk stuff. And so this is what we call designer materials. We can just make whatever we want, and which could have new properties that humans haven't seen before. And so it's this is the quantum phases triangle. There's colossal magnetoresistance, polar materials, semiconductors, insulators, electrically polarized materials, where if you just have it sitting, it's naturally going to be a positive and a negative. It just does it on its own. And then you have magnetism, and also the combination of you could have something that's magnetic and also electrically polarized, a multiferroic. And so these are really the exotic. I mean, kind of maybe not so exotic. These are like the properties of materials that we can now access by design, by choice, once we know how to do this crystal layer structuring, which all came from this Bragg's law, Bragg condition, appropriate for Nobel Prize, although this stuff came much later.
Yeah, this is like past couple decades, maybe, right?
It's hot topic. It's hot topic now, right? Past
Yeah,
couple decades.
yeah. Maybe someday some scientist will engineer will find, some cool application for this stuff for computing,
Yeah,
so we can
absolutely.
get our gaming rigs
That's right.
leveled up even higher. I mean,
Quantum
really,
gaming
that's what it's
rigs.
for.
That's
Yeah.
that's what it's for. It could be used for space travel, but give the people what they want. People want
Get the
gaming
people what they
rigs.
want. Yeah. I mean, we can go space travel, so we can go to Mars. so we can game on Mars.
Yeah, I mean, if you
That's
go
what
to
I want.
Mars, what are you going to do there? You're going to sit around. It's going to have low oxygen.
Mhm.
You're going to bring your oxygen mask and game.
Game setup. Yep.
Can you imagine the
And if the
latency?
gaming setup is super lightweight and easy to transport, hey,
Yep.
there you go.
Designer materials.
Yep.
Okay, so I think we gave two example. I guess one example was a fusion example of where Bragg's law became important. Another example is in condensed matter for Bragg's law building crystal structures, and our third example here is DNA, because it's through Bragg's law this n lambda is equal to 2d sine theta. That's the equation which is used to probe the distances between I guess the rungs of the ladder. That's a metaphor, and then also in this direction. And then also when you come at it at a funny angle, you get the distances between this guy and this guy. And so not only in fusion and condensed matter, but also in biology, Bragg's law has been high impact.
So for DNA, gosh, I would be very curious about the experimental setup for measuring the crystal structure of DNA,
I've thought about this too.
because like you need regular patterns for Bragg's law to function. So how did how did they line up the DNA molecules? I guess if you have a bunch of the DNA molecules, long chains, and they get all, if you have multiple of them, they're all twisted, turning, you get randomization of the orientation of the DNA, and maybe you can use the randomization with some assumptions baked in that you can get some magic angles still. I don't know how it would work. I'd be
I
very curious about the setup.
I have also thought about this, and it must have been a challenge. It must have been.
Yeah.
You must have seen on your screen on your X-ray detector. You're like, what is this? And so pulling
Yeah.
out the idea and that turned out to be right, that it's a double helix structure. Incredible.
Yeah.
Maybe we should do a deep dive in this and really like get down and figure out how this happened.
Yeah.
Because
I'm curious.
as you said, if we have a single strand here, I see how this has that periodic array. It's not like a nice square, but I see how the pattern is here. But if you have it like a drop of blood or something, you have DNA strands. It's all even in a single cell. You go down to the nucleus. These strands of DNA are just all sorts of whatever directions.
Right.
How
So
did
you
you,
don't, and you can't really control that. You can't come in with some tweezers. Let me just line it up.
nope,
Like it's not
nope,
going to happen.
can't do that. At least
Yeah.
not then. Yeah. So I don't know.
Yeah.
I don't know. Maybe
Yeah,
we should maybe we should dedicate a deep dive and figure out how that experiment worked.
Maybe that's a good idea.
Cool.
Okay.
See you next time.